So good morning, everyone. Today, my presentation is about how we are applying hypergraph learning to better represent molecules so that we can have better molecular property prediction. So
I'm going to do full screen. All right, good.
I can just scroll down.
Okay, yeah, we can do that.
Okay.
Sorry about that.
No problem. Oops. Okay. So the motivation for our research is basically the importance of molecular properties for drug design and drug discovery. Molecular properties, they're like physical, chemical, biological. They give you information about how the molecule interact and how the molecule behave. For example, a property such as toxicity tells us if the molecule is safe or not. A property like solubility, it tells us how the molecule absorbs, the absorption of the molecule. But the problem is that so in the web lab experiments, it's difficult to get these properties because these properties, they are extracting from molecular structures, and that's too slow to do it and costly. So that's why we need computational prediction models that will accelerate this drug discovery process. So for this computational prediction model, we need to convert the molecule into a machine-readable format. The most well-known one is graphs, because a molecule is just an interaction of atoms based on bonds. So we have atoms and bonds between them, which is translated to a graph where nodes are atoms and edges represent bonds. So this is the most well-known one. A second representation is fingerprints. Fingerprints, they're just binary vectors where we have zeros and ones, they're fixed size, and each one tells you that a specific substructure exists in a molecule. These substructures are also important because they give us more information about the property. Each substructure, they affect the properties in a different way. So these substructures can be rings, chains, functional groups, different ones, and we have different fingerprint types like MAX, PubChem, ERG, they're different types, and each one will give us a different chemical perspective. Now, since we have two different structures, we classify the existed models into two different types. Graph neural network models that are applied on graph. So the input will be the molecular graph that I presented, and it will go through layers where in each layer you then alert the information of each atoms, then combine them all into one graph representation and pass it to a predictor. So the good thing about these type of models is that they capture the atomic information, but they don't capture the information of different molecules. So they capture the information of one molecule at a time. Whereas in molecular property prediction, it's important to get the information of different molecules because it's known that molecules with similar structures, they tend to have similar properties. This is not captured here. The second type is a fingerprint-based type. So these are simple models. They just take the fingerprint binary vectors, pass it to a classifier, statistical or deep learning model, and you just get the property. Now, this is simple, but it doesn't give you really meaningful information. Like we said, we have different fingerprint types, and here it's not captured. They just take them as a whole, they combine them and pass them to a model, so it's not meaningful. It's not capturing any meaningful information. So we need a model that keeps these fingerprint type, the different information of these fingerprint types that capture the different molecular relationship and that give us the most important substructure for a property. So for that, we propose our model with a long name, Fingerprint-based Heterogeneous Hypergraph Attention Network, that basically models a molecule into a hyperedge and hypergraph that I will explain. So the molecular representation will allow us to capture the relationship between molecules, and at the same time, it captures the structure information, the substructures inside each molecule, and it will be passed to a neural network where it's gonna give us information about the most important substructures for the molecular property prediction. So we try to capture as maximum information as we can for the molecular property prediction. So it's there are two stages here, the hypergraph construction, which is the molecular representation, and the neural network. So for the hypergraph construction, so a hypergraph is just a generalization of a graph. In a graph, you only have pairwise connections. So we have nodes that are connected by edges, like I showed in the first two slides. And with a hypergraph, a hyperedge can connect multiple nodes. So we have many-to-many connections. And this is important for molecules because a molecule doesn't have only one substructure. It has many substructures. So a molecule can be represented as a hyperedge that will have many substructures, and the connection and the substructures, they are shared between different molecules. So this is just a formal definition of a heterogeneous hypergraph. We have three things: set of nodes, set of hyperedges, and set of node types. And it is represented as an incidence matrix that tells us if a substructure, if a node is in a specific hyperedge or not. So how it is applied to our model, we have three different types, so which are the fingerprint types, MAX, ERG, and PubChem. And each fingerprint bit, which is a substructure, is represented as a node, here the circular ones, and the hyperedges, they represent the molecules. So if you see in the graph, the hyperedges are molecules, the circles are substructures, and you can see that it's capturing the relationship between the molecules, and it has the different substructure information. So with this representation, each molecule will keep the three distinct fingerprint types, so it will keep that information. We're not combining them into one vector like existing models. We're preserving the chemical information of each type. So that's an important part, and the fact that we're representing molecules as hyperedges means that we can get the relationship between these molecules. So after constructing our heterogeneous hypergraph, we pass it to our neural network that has mainly two stages: the hyperedge to node attention and node to hyperedge attention, then fusion and classification. So basically in the first stage, we just so it's the hyperedge to node attention, which the information just flows from the molecule to the substructure. So each substructure will get the information of its molecule. And here it is weighted, meaning that, really? Okay, and here it's weighted, so we get the most important molecules for each substructure. And here the information flows from the substructure to the molecules, so it's weighted too, and we're getting the most important substructure for each molecule. And then we combine everything, we pass it to classification.
My bad.
Okay. So yeah, so basically that's it. We have two different flows of information from molecules to substructure to molecules, and it's weighted. We know which substructure are most important for each property, and we pass them to a classifier. Yeah, so these are technical details. Now, we tested our model on different types of data sets. We have binary classification, multi-label classification, regression, and these data sets, each one has a specific properties. We use ROC for classification, RMSE for regression as metrics. We have different number of molecules. Yeah, it's a mixed data set. So for the results, we compared our model with fingerprint-based models and graph neural network-based models. So for these classification datasets, our model is outperforming. So it's outperforming 2 out of 3. And if we take the average rank, with 1 being the best, it is ranked first. And if we take the second type of classification, which is about toxicity properties, we find that our model is outperforming only the fingerprint-based ones, but it's not outperforming the graph-based ones. Here it means that these toxicity properties, they depend more on the atomic level information and not the fingerprint level information. So for the regression data sets, here are their values. Basically, our model is outperforming the state of the art. And we did an ablation study where we wanted to see which fingerprint is more important. And for each data set, it depends. But when we combine all of them, we always have better results. But here you can see that we have MAX, ERG, PubChem. Each one will have a different output for each data set. So really keeping the information between them distinct is important because each one will have a different effect for the prediction. So we created a model that unifies the different fingerprint types and molecules into one heterogeneous hypergraph. It keeps the relationship between the molecules, and we pass it to an encoder that will get the most important substructures for the property prediction. It's performed well, but of course we had some limitation, especially for the toxicity property dataset like we show. So we need to incorporate more atomic level information to this model, and that's our future work. Thank you.